So, good afternoon, everyone. We'll start today's lecture. This is the third lecture on statistics in research methodology. It is audible to all of you, no? Today we are going to discuss error propagation rules as we had discussed in the last class. Before going to the error propagation rules, we will have a recap of the previous two lectures, 1 and 2. Initially, we had discussed in detail regarding the roles of statistics in both daily life and research. We have seen various facets of statistics being utilized in each and every step of research. Then we had discussed in detail regarding the various physical quantities, the ways of measuring the different parameters which affect the measurements, and how we can represent effectively the results of measurement. Later on, we had gone to the accuracy, precision measurements. We had done a few exercises to get clarity regarding these two concepts. And in the second lecture, we had discussed significant figures, place value of digits, rounding of rules, and a few of the exercises we had done during the discussion. And in the last slide, we had given a few of the exercises for you to have practice on them. So these are the answers to those questions. Whoever has undertaken those questions, they can have a cross check between your answer and the answers given over here. I will just keep this slide for 1 minute so that all of you can have either screenshot or you can take it later on. All the answers for the first two questions are combined in this slide, and in the next slide, the answers to the third and fourth questions are given. In the fourth question, the question was to convert from scientific to the decimal notation, keeping the significant figures, number of significant figures as identical as that of the scientific expression. But at some point of those questions, you find that it is not properly expressed in the decimal notation. So here again, it emphasizes the requirement of expression of data in the scientific notation only. So these are all for the previous two lectures. Now we will go ahead with today's discussion, that is regarding the propagation of errors. The rules pertaining to the error propagation are utilized for this standard deviation, uncertainty propagation also. Though the terminology is different, error propagation rules are applied to propagation of standard deviation, uncertainty also, which further will be reflected in the ultimate precision or the number of significant figures in the final expression of your results, which you present towards the third person. So generally, if you can consider, if you take a function u, which depends on various parameters such as x, y, and z, these are considered here as variables which fluctuate. These variables fluctuate randomly as well as independently. This independently, that condition is very important. If the variables interact with each other, x, y, z, these are the variables, input parameters. If they interact with each other, the conditions change, the error propagation rules get modified. Here we have taken the simplest of that. U is a function of x, y, z, and the general propagation says that the variances in the case of addition and subtraction, you can see that the variances are additive. Generally, what we do is we see the variation in the function u as with respect to that of individual contributing factors such as x, y, z, keeping the other parameters fixed. So we take partial derivative of the function u with reference to the parameter or the input parameter which is getting fluctuated. That way we get the propagation. The general rule, mathematical formula is given on the right-hand side table. When we do simple mathematical operation like addition or subtraction, you can see there is a function. For example, a function is given here, u is equal to x plus y minus z. Herein, you can see one addition operation, one subtraction operation is also there. So if you take partial derivative of u with reference to x, then the derivative will be 1 for this function. Similarly, for y also you will get the same number. For z it will be minus. But since we take the squares and take addition, we will see that the total standard deviation for the function u will be expressed in terms of the variance. Square of standard deviation, we call it as variance. The variance of this resultant of addition and subtraction is nothing but the sum of the variances of the individual contributors. Okay, variance of the resultant is the sum of the individual variances. That means in another way you can say that absolute variances are additive. Even though we do a subtraction operation, the final uncertainty or standard deviation gets added up in terms of their squares. Another set of operation here, multiplication and division are considered together because the impact or the effect of these operations on the final standard deviation, propagated standard deviation, is similar. One example is given over here. U, a function, is the resultant of product of x and y, which is again divided by another variable z. Then here you can see that the squares of the relative standard deviations get added up. Here again, the same way we take partial derivative of the function with reference to 1, keeping the other parameters constant. The same rule which is given in that box on the right hand side top, that rule is applicable to everywhere. Depending on the operation, you have to do the partial derivative and substitute in the original equation given on the top. So after substitution, you get that the square of the relative standard deviation of a function obtained by multiplication or division or these operations together will be equal to the sum of the individual squares of the individual standard deviation. So if you take square root, then the function will look like this. And if you want to calculate the uncertainty or standard deviation, S represents either standard deviation or uncertainty. Standard deviation was the nomenclature earlier used. Now we frequently practice the word uncertainty for S. So if you want to calculate S, that is standard deviation in the function U, take the square root on the right hand side and multiply it with the resultant U. That will be the absolute standard deviation of the final result. SU will be U times the square root of the function that is given on the right hand side. All of you will be practicing these equations given in this as well as the previous slide. We will have practice session in the exercises in the forthcoming slides. So you will get familiarized with these equations, and later on, whenever you do any mathematical operation on your results, measured results, this propagation of errors will be applied to try to practice these things. When we do multiple measurements, definitely we take the same repeated measurements. If we take, finally, we represent the result in terms of mean of the several such repeated measurements. Normally, mean is calculated by taking average of, say, if we are taking n measurements, it is nothing but sum of the individual measurements divided by the total number. Here again, the same way we get the partial derivative. All of you can appreciate that it is very simple to do the partial derivative because all of the rest of the things are kept constant. So the partial derivative of the mean with respect to individual function will be 1 by n. That is the coefficient of each of the terms. Then the final propagated uncertainty will be nothing but the squared partial derivative plus s of standard deviation of the individual functions. So this way it can simply go ahead and you will get that the square of the standard deviation of mean is nothing but 1 by n times the standard deviation of the individual contributors. So if you have to calculate simply the standard deviation of mean, it will be root 1 by root n times that of the standard deviation by the individual contributors. So these formula you can directly apply to wherever you encounter such calculations involved in your measurement and final expression of the results. So we have seen three different cases. One is a set of addition, subtraction. Another is multiplication and division. Another one is calculation of mean. Similarly, we can extend the same way. If there is a weighted summation or difference, you can have the corresponding propagated uncertainty or propagated standard deviation as given in the topmost box. The topmost box black font color, U is AX plus BY. X and Y are the contributors or the measured quantities. A and B are the constants corresponding to those measured parameters. And the uncertainty of U, square of the uncertainty of U is given there. When we do multiplication, division, here both are separately given. Though since we take the squares, the negative terms will not remain. It will also get added up. So always uncertainty gets propagated in that way. Relative uncertainties, never do they cancel out. That is the thing you have to keep in mind. And the second box, the things have been well explained here. So we go ahead. When we have a function u, which is a power of a variable x, the power form is given here, then the relative uncertainty in that function is also given here. So all these formulae you can make use of wherever you do such operations, either addition, subtraction, or multiplication, division, or power functions. Similarly, there are several other mathematical functions. For example, if you do the calculations, for example, when you are measuring radioactivity, you will see that the activity keeps on decreasing exponentially with time. So there will be an exponential function. If you want to apply this error propagation for exponential function, all these equations you need not have to by heart. These are available. You have to utilize it appropriately. Wherever you do an exponential operation, apply this rule. Relative uncertainty in the exponent will be the exponent times the uncertainty in the contributing factor or the contributing parameters or the measured quantity. Similarly, if the constant is raised to some power, then the formula gets reoriented slightly. That is also given in the second line in this box. Another function is logarithmic expression. Here again, the uncertainty calculation goes ahead like this. So when you are doing multiple operations, combined operations in a particular set of measurements, you have to follow systematically, stepwise, one by one. If you follow the rules properly, systematically, if you do, then you will smoothly land up in the final standard uncertainty. If you try to combine the steps, maybe you may miss out some important points. So it is better to be patient initially, formulate your entire measurement step and apply the formula for each of the parameters, each of the expressions, and arrive at the final uncertainty, final standard deviation. Trigonometric functions like sine, cosine, there again, all these come from the original equation. Take the partial derivative and square it and multiply with the individual standard deviation. The original formula comes from there. Okay, everywhere. So we have seen addition, subtraction, multiplication, division, power function, exponential, logarithm, and trigonometric functions. These are the general ones we encounter during the calculations in research daily. If anybody wants further clarification regarding any other function, we can have those two also. Now, these are a few numerical examples pertaining to those rules. This is to give you a better feel of those derivations which we have discussed just now. So here in the left hand side box, when you see the screen on the left hand side box, there are two expressions given. Before proceeding for the propagation of significant figures or uncertainty, you have to see that the parameters which we do these operations, they have the same unit. They have the same units in the expression. If not, make the uniformity in the units of that parameters, then you proceed with the operation, mathematical operations. Two quantities bearing two separate units, try to avoid addition or subtraction directly on those. Okay, if the one quantity is given in centimeter, other is in meter, convert either of them into centimeter and do proceed. Otherwise, you can convert both of them into meter also. Here, both the quantities are given in centimeters, so you can simply add those things. If the answer, normally the general advice is that express the quantity in terms of the value plus or minus the standard deviation, then the unit. Here in these examples, the plus or minus standard deviation expressions are not given. If those are not explicitly given, presume that the last digit, as we have seen the significant figures, the last digit is uncertain. The place value into unit 1, unity 1, that will be the uncertainty pertaining to that one. That rule has been followed, and final calculation is shown here. All of you can practice and come out with your results. Check with this, whatever is given over here. Okay. In addition and subtraction, you can just have a thumb rule. Absolute uncertainty is conserved. Otherwise, very easy way to check out is the result of your final operations will be bearing same number of decimal places as the number which has got fewest decimal places. So whichever number has got fewest decimal places, it will have the maximum uncertainty. Uncertainty will always show you the maximum variation or fluctuation in your measurement, the least precise measurement, having maximum uncertainty. That will be hindering your final refinement of data. Okay. So since the plus or minus standard deviations are not given here, we see that the last digit is uncertain. Accordingly, the standard deviation is given here. It is always better to express with this standard deviation so that the reader also can appreciate the measurement uncertainties. On the right hand side, another numerical is given. Here again, you can, as we have discussed in the previous class regarding the significant figures and the rounding of roots, those we will not discuss in today's class. We'll just see that the propagation of errors is applied over here. Okay. In multiplication and division, the error propagation rule says that in words, relative uncertainties are conserved. The contributing factor, whichever holds the maximum relative uncertainty, the final results also will have that much of uncertainty. That will have the major hold on the uncertainty. So these numericals which are shown in the screen, there are 3 numericals for multiplication and division. All of you can have a hands-on experience by doing this. Try to remember that in addition to the final result, you put in the variation or fluctuation or the uncertainty as well as the unit of the measurement wherever applicable. Okay, so these all numericals, all of you can practice. Later on also it will be visible to you. So once you practice, cross-check your answers with those shown over here. In addition, subtraction, there won't be any confusion. In multiplication, division, what you have to do is follow the error propagation rule. Relative uncertainties also you calculate and find out whichever factor has got highest relative uncertainty. The result will also follow its trend. So in words, whatever we have seen in the previous slide, in words, in addition and subtraction, the absolute uncertainty in the result must be equal to the largest absolute uncertainty among the components. So that will be visibly possible for all of you. When we do multiplication and division, relative uncertainty in the result must be equal to the largest uncertainty among the components. Here, no, it is not just by counting the number of significant figures. Sometimes you may land up in wrong result. This example tells you like that. You calculate the relative uncertainty, then only you proceed. Otherwise, what will happen? If you simply count the number of significant figures, for example, ratio of length to breadth of a rectangular table. Length is given 102 centimeters, breadth is 99 centimeters. If you just count the number of significant figures, you will see that the length has got 3 significant figures, breadth has got 2 significant figures. Whichever has got lower one, then you will follow the rule and finally what will happen? 102 by 99, you will reach as 1.0. That means 102 by 99 will have a value equal to 1.0. That means 99 equal to 102. That is wrong mathematically. So be cautious while doing this multiplication and division operation. Take the relative uncertainties and the relative uncertainty, whichever has got higher relative uncertainty, follow those rules. The squares of the relative standard deviations get added up in reaching to the relative square of the relative standard deviation of the function which you obtain during this operation. For example, when you divide 102 by 99, if you follow the rule strictly, the result will be 1.030 plus or minus 0.015. If you do not follow it exactly just by counting the number of significant figures, misleading results may occur. Okay, this point should be clear to all of you. Multiplication and division, you have to follow the relative uncertainty conservation rule. Okay, here in this example, one equation is given, somebody is measuring the signal which is proportional to concentration, and there is a slight interference from the instrument that is called the intercept. So herein you can see constant into concentration plus I. Multiplication operation as well as some addition operation. So herein you have to apply the rules in individual steps and arrive at the result. Okay. So if you have to calculate the standard deviation of the concentration one can easily calculate. That's nothing but the signal minus intercept divided the whole divided by the calibration constant K. So that also all of you try to follow. I think all of you are able to follow these things. What we are applying here is the error propagation rules for various mathematical operations as applied to your day-to-day research. If somebody is measuring some concentration using instrument, wherein the instrumental parameter, instrumental signal is having some functional relationship with the concentration, definitely there is an instrumental initial, some people say as background or intercept for the minimum signal, sometimes the dark current, those will be there. So that way the signal, measured signal is given as a function K into a constant K into C. This constant is called the calibration slope for most of the instrumental measurements, and the I is called the intercept. So from this one can easily calculate C concentration provided you have the slope in hand and the intercept. So that way the calculation is shown in detail. Each and every step of this calculation is shown here. Only thing is that you also try to take a pen and paper and practice yourself. Okay. So that later on independently you can finally, after arriving at the propagated uncertainty, This is the way you will be representing your final result. Okay. The place value of the standard deviation. Normally, standard deviations are expressed. The general rule of thumb is that you express the standard deviation up to two significant figures, and up to the first significant place value of the first significant figure in the standard deviation. Here you can see this two in the standard deviation. The place value is one's place. So your result will have the number 6, which is corresponding to the place value of 1. So that way we round up. See the place, first you have to round of the standard deviation up to two significant figures. Then find what is the place value of the standard deviation. Up to that place value, you round the average or the mean value. This is the presently prevailing rule for expression of any measurement result. Okay. These are a few, some 2-3 examples for you to practice. All of you can quickly try to do this. There is one expression for summing up for the numerical values 10.4, 100.016, 0.014, and 10.02. As their uncertainty or standard deviation is not given here, what you can do is you can do the mathematical operation, arrive at the result, and confirm that the least significant figure, when you express the result, the digit which is on the rightmost side of you, when you are facing the paper or your screen, rightmost side, that is the least significant digit. We discussed in the last class, least and most significant. So in that place value, there will be fluctuation, if at all the uncertainty is not explicitly given. So all of you might have done this addition operation, and now you can also check the result. The proper expression will be 120.4 with one point after the decimal, and the uncertainty, since it is not given, you can write that. This is following the significant figure as well as the rounding off rules, which we discussed in detail in the previous class. Here we are only applying the error propagation rule. We do the mathematical operation and apply those rules. This another example, somebody is doing the measurement of density of an object. Mass and volume were also measured. So the density is nothing but mass by volume. So you can also try to do. This is just a division operation of mass by the volume, 29.1143 by 25.0. Then all of you will be able to do this operation very efficiently. The thing is that how many digits you have to express in the final, you are allowed to express in the final presentation of the data. That will be presided over by the least precise measurement, or the number having lower number of significant figures in general. When we are doing this division operation, keep in mind that relative uncertainty is conserved. So you have to take when you are calculating the final uncertainty, take the relative uncertainty of the individual contributors and propagate it as per the rule we just discussed. So then if you follow the rules properly, you will see that the choice E is the answer. All of you may try to do this, and if at all there is any confusion either in this class or in the coming class, you may please discuss. Towards the end, we dedicate some 5 to 10 minutes for such discussion. All of you are requested to try to do all these things, and if at all you have any specific queries or any specific examples wherein you want discussion, please bring those also so that others can also appreciate. The first two ones are very, very easy for you to do because they were almost single step measures. Now in the third one, the expression shows that there are 2 multiplications in the 2 or 3 multiplications in the numerator. one subtraction operation. Then you have one addition in the denominator, then another division in their division. Ideally, what you have to do is do stepwise. Do not round off in individual steps. Go to the final one and do the rounding off. Do stepwise. If at all the uncertainties are not explicitly given, presume that the least significant digit is uncertain to the place value. Hope all of you are able to follow whatever we discussed. This numerical is explicitly given in this slide. Each step is given the value, the standard deviation is given as u in the value, that is uncertainty in the value, then the relative uncertainty, square of the relative uncertainty, the summation, each and every step is given here. When we do a multiplication or division operation, either of these operations, you follow the relative uncertainty conservation rule. So the same applies to step 2 also. In the step 3, you do some subtraction operation where absolute uncertainties are conserved. Square of the standard deviation, that is variances. Absolute variances are just additive. So here in the third step, where you do subtraction operation, you need not have to calculate the relative value. Relative, by the relative word is also clear to all of you. Anything relative means there is some reference to which you are taking care of that value. So if I say relative, percentage is one relative term. So that means every value is compared with the one base value. In the case of percentage, it is 100. So relative uncertainty of your measurement means measured value and the standard deviation or uncertainty normalized with respect to that value. So your uncertainty divided by that value. That is the relative uncertainty. In the fourth step, it is similar to the third step, addition operation. In the final step, that is the last step, you do a division. The same rule as for the steps 1 and 2, you can do. So here in the final step, you will have relative uncertainty propagation. The operations are very simple. Any even 9th, 10th standard student can do this operation. The only thing is that you have to follow the rules systematically, stepwise. Then the life will be very easy. You will land up in the appropriate representation of your result. Okay. Then there won't be any confusion. And in research, it is very important to document your measurement as well as the steps involved in all these measurements. So if you document the procedure of your propagation, error propagation, later on, if either yourself or your guide or a third person wants to cross-check your results, it will be easy for them to follow this one. These are this slide is especially a screenshot of the Excel calculations which I had done for this class. So you can either make an Excel sheet or Google sheet for similar calculations. Then later on, if you are doing similar operations, life will be easy. You have to just simply change the input parameters. And the uncertainty values, many a times, it will be like measured uncertainty by repeated measurements. Sometimes it will be taken from the literature. That we will discuss in the coming classes, where from this uncertainty value comes for measured quantities. That also we will discuss in detail, so that the origin of this uncertainty also will be clear to all of you. If anybody is not able to follow, please write in the chat box. Towards the end, we will have a discussion. This is just for you to get better grip on the significant figures, rounding off, and the error propagation rules. These are the things we discussed in the previous and the present class. So, significant figures are well clear to all of you. Please try to do these things yourself. Okay. In the next class, I will give you the answers to these questions so that all of you get a chance to do it independently. Rounding off also up to 4 significant figures. I hope all of you understand 4 significant figures. Start counting from the left one to the right, number of significant figures, rounding off also rules we have discussed in very detail in the last class. In the third question, the error propagation rules, which we discussed just in this class. The third one is new to all of you. So the steps, as I discussed in the previous slide, each and every step is discussed in detail because this is new to you. All of you can try to do all these steps. Try to do stepwise, though it may take a bit of time, a few minutes of you. Try to practice it. Once you get the confidence, later on you can rely on Excel or Google or calculator or computer, whichever you follow normally. But try to do yourself, get a grip, get a feel. Later on, then you can feed in the input in the whatever form of calculation you do. One or two times you do yourself. Each step you divide the total operation is divided into individual small steps like addition or subtraction or multiplication or division. Sometimes power operation, exponential or some trigonometric functions. All those you can include in this one. The error, form of error is discussed in the previous slides. So all of you can have a copy of these slides and apply to, if at all you have already started research, if you have any such calculations, try to apply to your problems and come up with the results. So that will be useful. If anybody wants to discuss in detail for a particular specific problem, be in touch with me through the email. So these are the individual steps discussed in detail. Since there is not much of extra points in this one, I'll not go into the details. The final result, the error propagation, significant figures, rounding off rules, everything is followed as per the prevailing rule of expression of the final result. Keep two significant figures in the standard deviation. Accordingly, the result is expressed here, and up to the place value of the first significant figure in the expression of the standard deviation, your mean value or your calculated value can also be expressed. Beyond that, it will be an overestimation of precision. Okay. Logarithmic function, as we have discussed in the previous class, significant figures will be counted only after the decimal point. So that way you express the result. Okay. This one is also a worked out example for all of you to practice. The results are the final calculation and the steps involved are shown here. In the next mouse click, you will see the answer. It is a very simple problem to calculate the area of a circle from the measured quantity of radius of the same. And the uncertainty is also given here on the right top. The idea is how to express the final calculated area of the circle along with the uncertainty pertaining to it. So the value of pi is not substituted here. All of you know that it is nothing but 22/7. You can directly do that also, incorporate that also, since it has got not much significance in this particular discussion. I have not substituted for pi. You people can do substitute for pi and come up with the result. This one is for all of you to do in exactly the same way as we have discussed in the top question. So do this problem yourself. The expression of the radius, the radius and this in height. all the things are given here. Length as well as the height of the circle, everything is given. So length of the chord as well as the distance from the chord to the circumference of the circle. All the input parameter values are given. The expression to find out the radius is also given. What you have to calculate is the radius and the uncertainty coming out from two different measurements. You can see that the heights are almost same, the lengths are almost same chord, but the heights are different. Okay, so you can calculate. The result I'll discuss in the next class. So you people can note down this question and get a practice on this. We go ahead. This is similar way. A few more examples are shown here to find out the area of a triangle, the equation. What you have to do is construct the equation pertain, construct the relationship between the measured quantities and the ultimate data or result which you want to express, and then measure the individual parameters, find out what is the contribution from uncertainty, propagate them. Okay, propagate means follow the error propagation rule, which we discussed in detail in the present class. Okay. The expression for finding the area of the triangle is base into height divided by 2. So the uncertainties are given here. So you can see that the uncertainties are given in plus or minus value. The uncertainty in the height is numerically larger than that in the base. However, you will see that the relative uncertainty, since here the multiplication operation is involved, you will see that the relative uncertainty is lower, because when you take relative term, the denominator will have the original value, the contributing value. The relative uncertainty in height is lower, and so the contribution due to a variation in the measurement of height will be lower in the final calculation. So that means, since the numerical value of base length is smaller, if you have a choice to do in between two measuring tools of the length of this base and the height, you have to opt for the better precise tool for measuring the base of the triangle. This is what is conveyed in this numerical, not only the calculation. If you have a choice to select in between several measuring tools, as we discussed in the very first class, measuring tools, if you have several measuring tools, which tool to use in which context? You have to measure the length only in both the cases. But wherever you have smaller length measurements, go for a better precise tool, as the uncertainty will hold or will have larger hold. Relative uncertainty will have larger hold if you do repeated or several such mathematical operations. Anyway, it is not direct. Anyway, research when you do, it is not a single step process. You will have multi-stage calculations in. So in each and every step, if you are careful enough, you can reduce the variation or uncertainty and come up with very good results. So the same measurement, if two people do with the two different measuring tools, one will say that the one having lower numerical value of uncertainty will have better precision. So it is like clarity in the choice of the measuring device, which we discussed in the very first class. This fourth question is also in the similar line. You have to comment on which contributor have got higher share of the uncertainty. As we discussed in the third one, similar way you can do this calculation. These calculations everybody can simply do. This is nothing but multiplication of the length and width of the this thing, triangle. So directly you can do. Okay. And finally, comment on which parameter is contributing to larger. If you compare the absolute uncertainties, you will see that both length and width have got similar absolute uncertainty. But since it is a multiplication operation, you will see that the contribution from the length is only 6% of the effective contribution coming out from width measurement. So width measurement should be more careful when you do this final calculation. This is a recommendation or the formulation of how to represent the final results after applying the error propagation rules. Normally, the rules we follow presently is those from ASTM, American Society for Testing and Materials. The rule, the title is E2930. This revision was reapproved on 2019, year 2019. So every 5-6 years, the rules get revised or revisited, and if at all there is any dispute or clarification required, the rules get modified. So it is due time for this rule to be revisited. 2019, the rule was reapproved. So maybe in this year or next year itself, the rule may get amended. So keep a watch on such website, authentic websites. For example, for the chemistry fraternity, IUPAC is the website wherein you can have reliable references regarding such clarifications. Or if at all you are in the general fraternity ASTM website, you can see ASTM E29 2013 was the first publication of this expression of results. So you can have the original document also or not. You can have the approved one in 2019. The relevant portion of that document is only given here. And whatever is required for us to follow, that is given in red font color in the third bullet point inside the box. So round the standard deviation to two significant figures, two significant digits. Then round the average to the same first place value of the significant figure in the standard deviation. As all of you are familiar with the terminologies like place value, significant digits, standard deviation, I will not elaborate on each of these terms. And if at all the first significant digit in the standard deviation is unity 1, then you can have one more digit in the average of the final expression. This is the rule prevailing now. Anytime we may have a revisit of the rule, that time we may amend this one, if at all there is any change. Okay. And whenever your measurements are at the primitive level of your measuring device, sometimes your measuring device fluctuation or the background or the dark current itself is much larger than your signal. You may not be able to detect the quantity or parameter which you are trying to measure. So that time you declare that yes, I am not able to see the signal properly. Do not try to manipulate. If at all, even if it is slightly above the background of the instrument, sometimes visibility or the measurability may be poor. So that time you declare that it is a feeble signal, I am not able to completely quantify. So what you do, you say that it is above the limit of detection, but below the limit of quantitation. These terms we will discuss in the forthcoming classes in detail. Now you be informed that whenever the signal is within the fluctuation of the measuring device, you never report a numerical value. Whenever it is slightly above but not visibly separate from the background, then also you never report the numerical value. Then you say that it seems that the signal is there, but quantification is not possible. Whenever the signal is visibly separate from the background and it is 10 times the standard deviation of the background, from that onwards only your value will be reported, which will have reliability in the final expression. So keep in mind, in the last table I have given, wherever you can report the value with numerical quantity, wherever you can only give an estimate, give an idea whether something is present or absent, some signal is visible or not. It is not that always you come up with numerical value of the measured quantities. Sometimes we say that it is either present, not present. If at all present, then only the question comes whether it is quantifiable or not. Even if it is present, whether my measuring tool allows me to do the quantification, that is discussed in this table. So this also you try to follow. And these problems are for you to do yourself. Here in the first one, there is slight difference. In the initial slides, we had discussed the function as we had defined the function of u as a parameter varying with respect to x and y. Here in the first one, the terminology is slightly different. Here, x is the parameter which is quantified, calculated. Here, the input parameters variables are u and y. There is a slight difference in the nomenclature. So that also you try to keep a watch whether the nomenclature is properly followed or not. These are from different references. So some people use X as the variable, some people use U and V as the variables. The second and third problems also are very simple to do as we discuss in detail in the other ones. And this will give you a grip where to give stress, where to be very careful while measuring, where you can have slight relaxation in the measurement. Second one is to find out which some person is measuring resistance of a cylindrical conductor, calculating the resistance via measurement of its radius and the length. So which parameter to be measured more carefully, more cautiously, so that the results will be more reliable. You have a choice between the measuring tools. And the third question is regarding the refractive index of medium using the Snell's law. The equation is also given here. Whoever is not familiar with this Snell's law, equation is given here. All the input parameters are given here and has to calculate the N2. That is the refractive index of the medium, second medium. So N2 will be nothing but N1 sin theta 1 by sin theta 2. All the values are given. So all of you have a practice on these problems as well as a few, 2-3 problems in the previous slides. Now, this is the last slide for today. We will go to the chat box and see if anybody wants to discuss anything. If anybody wants to discuss, that we will do. PPT was not visible in between. PPT recording you will be getting maybe in a day or two. So as and when you get the PPT, try to do those things. Any doubts or any suggestion or any clarification, you can write in the chat box. Till then, I'll just summarize. We discussed in the previous and current class regarding significant figures, rounding of rules, error propagation rules for various mathematical operations like addition, subtraction, multiplication, division, power, exponential, logarithmic, and trigonometric functions. And a few examples wherein each and every step was discussed in detail and a few for you to do. Anybody wants to discuss anything, you can write down in the chat box. Or whoever has got everything clear, you can leave also. Whoever wants to discuss further may stay back. Next class will be on day after tomorrow. So by that time, try to attempt those questions and come. If while attempting those problems, if you feel that you are not able to do, you may please be in touch with me via mail. My mail ID is there in the first lecture itself. psremya@barc.gov.in. Phone number is also given there, 20224 for the extension. Otherwise, 02225590224. If there is no further doubt, then we will leave for the day. Nobody has written any doubt, then we will leave for the day.